Now that we have taken a look at some of the more complicated mathematical aspects of simple harmonic motion, we're just going to take a look at what simple harmonic motion is in general. So we have some examples here of bodies that undergo simple harmonic motion. So the key one and the one we've been looking at is a mass vibrating up and down at the end of a spring. Be careful when you give an answer. You do need to say that it's vibrating up and down, because if it's just sitting like this, obviously there's no motion, let alone simple harmonic motion. Another common example is each prong on a vibrating tuning fork. As these prongs move back and forward, there's that little bit of dampening that appears, so they go back and forth and then they settle back to their equilibrium position, and that back and forth is simple harmonic motion. This one is an interesting but more complicated version. It also gives us a bit more of insight into this tricky omega thing and how it relates to simple harmonic motion. So if we have this thing here, we have light shining in on a rotating turntable, and we have an object here stuck to the wheel. As the wheel goes around, obviously so too does the wheel. But if we look at the projection of that image on the wall, the shadow of that object goes over and back with no dampening, but over and back, and that therefore it shows simple harmonic motion. So if it's going to be over here at P, it goes over here, it goes back to P, it goes. So as we look on the wall, this 2D reflection, this 2D projection is simple harmonic motion. Another one is a small angle of swing of a pendulum. So if you're typically on a swing, just going back and forth, that back and forth is also simple harmonic motion. The tides coming in and out every 6 hours, another example of simple harmonic motion. So tides go in, tides go out, tides go in, tides go out. So that back and forth is your simple harmonic motion. And then a displaced magnet suspended and swinging horizontally as long as it's aligned north to south. So in the picture here, we have the magnet lined up north to south. If you bring the magnet over this way a little bit, it's going to be attracted back towards the north. It's going to miss the mark though, it's too much velocity, and it's going to come back over here. Then it'll go back over again, then it'll come back to position, so it'll keep accelerating towards the center, hitting the point, and then the momentum carrying it through, and then it'll go back and forth, back and forth. So if there is some dampening, that will again settle back to the original position, but the swinging over and back, that's our simple harmonic motion. So there's some of the common examples. Remember a few of those for SHM. As a recap of what we looked at before, and the key things you need to remember. If we take a look at this particle that's moving over this range A to B. So we have A here, B here, and then we have the fixed point at the center, that's O. The mass is always accelerated towards the center. So when it starts off at A, it's going to have maximum acceleration. It accelerates towards O. As soon as it gets to O, then it's going to start decelerating, because it's slowing down. Once it gets to B, it's stopped, and then it's going to accelerate backwards. So the mass is always accelerated towards the center, and we'll see this in our simulation as well. At the center, the acceleration is 0. It accelerates towards center, but once it gets at the center, it's got no more acceleration. After that, it's going to begin to slow. So again, the strain of the spring building up, builds up, slows down, then shoots back, and then it builds up, builds up, builds up. The velocity and the kinetic energy is at the max at 0. So it's got acceleration into the center, so it's getting faster, faster, faster. Afterwards, the acceleration is back this way, so it gets slower, slower, slower. So at 0, at the center, the velocity and therefore the kinetic energy is max, because kinetic energy for any mass is based on speed. Then the acceleration and potential energy is a max at A and B. So you got your max acceleration here, your spring about to fire off, or your spring about to recoil. That gives you the max acceleration, and that gives you your max potential energy. So your potential energy, mgh, it's going to be most at A and B, or the top and bottom in the normal up and down spring, but we can also have the back and forwards. Amplitude is another thing that we'll look at later on. It appears in waves, and it's also important here. What amplitude is, it's the distance from the rest position or the equilibrium position to the extreme. So the amplitude there and the amplitude here is the same distance, so it's from the rest to the extreme position. It's not the over and back, it's not the full thing, it's just the amount it moves from its regular position. So from its resting position, how much it moves. So again, we got the summary here. B is 0, A is max. B is max, A is 0. B is 0, A is max. And A is always directed towards the center, and that's your restoring force that will accelerate it back towards the middle. So we got to look at some more of these key terms and the key vocabulary we use when we're talking about SHM. So the terms used here, they're identical to those used to describe waves. We'll be looking at these again when we study waves in more detail at a later date, but for now we need to learn them for our use in the SHM course. So an oscillation or a cycle is over and back. So it's A over to B and back to A. So it's your full swing over and then back. That's an oscillation, also called a cycle, and we can use those terms interchangeably. As we analyze this motion over and back, we would like to have terms and expressions and quantities so we can measure all of the things and understand a given problem. So the time taken for one oscillation is known as the period, and that's given the letter T. T is measured in seconds as it's a time. So however, going over and back, A and B, A to B and back to A, that's the oscillation. How long that takes, that's the period. The frequency then, again, we could have our over and back, however long that takes, but we would need to see how long it takes to go over and back. That's kind of the period. But then if we want to see how many we get in a second, that's the frequency. So the frequency is the amount of cycles that happen per second. So how many cycles you get every second. The unit is the per second, and it's also known as the hertz. So hertz, anything that's frequency is hertz, and it's the per second. So if we look at the definitions to create formulas, as the period is the time taken for one oscillation, and the frequency is the number of cycles per second. So it's how many cycles you get in a second. That's your period. So we have T for a period is 1 for the 1 second divided by the frequency, how many you get, and that's a period. That's a formula for the period. Likewise, if we look at our definitions again, the frequency is the number of oscillations every second. So how many over and backs you get in a second. So the period is the time taken for one cycle, so frequency is 1 over T. So it's how long it takes to happen divided by 1. If we look at a couple of examples for this, if the period was 2, so it took 2 seconds to go over and back, F will be 1 divided by 2, so it will be a half. So we'd get half a cycle every second, so it will be 0.5 hertz. If we get 3 cycles per second, if we get 3 cycles per second, that will be the frequency, so that will be a period of 1 over 3. So it will take a third of a second to do the period. So if you have 3 cycles every second, that's what the frequency is. So it will be 1 over 3, which will be a third of a second. If we have half a second to do an oscillation, so it goes over and back in half a second, that will be my period. So F is equal to 1 over a half, which will be 2. So it takes half a second for a cycle, so that means we have a frequency of 2 cycles per second. So they are naturally enough occurring formulas, and we should be able to use them and understand them. There's a couple more formulas for the period though. So another one is given here. We don't need to know where it came from, but we do need to know it. So the period is 2 pi over omega. So that's omega appearing again, and this is a common formula you need to use in your calculation questions. You can kind of think of this as distance over speed. So it's kind of 2 pi as the distance that you cover, omega the time it takes to cover it. And again, if we take a look back at this picture here with the projection, this would be our full circle, our 2 pi. This would be our angular velocity as we look at in circular motion. But for now, we just accept this formula and we'll use it later on. This omega here is the same as the one we used before. So if we find the omega from this, we can use it in the previous formula for simple harmonic motion and vice versa. You can kind of think of it as distance over speed. It might be a little bit useful. But what we're going to do now is we're going to look at a bit more of the simulations, and we're going to take a look at this period trace. So if I take my mass and I push it upwards, the trace will time how long it takes for that to occur. So you get the down and the up and the down. That's your one oscillation. They're going about the center. So that's the time it takes for one full cycle. So this is our thing that's happening here. I've put the gravity to the moon, so that's why it's going quite slowly. So that is our period. If we want to time this, we can do it reasonably easily. If I start it when it starts, stop it when it stops, we get the period of, I guess it's about 2 seconds. So this period is something we're going to look at later on, but that's what the period is, the time taken for a full cycle. The more of those we get, the number that pass every second, that's your frequency. So if this takes 2 seconds to do a cycle, then using my formula here, the frequency will be 1 over 2, so that's half a wave every second. Half a cycle, half an oscillation every second. If I adjust my gravity, and again, this will affect where the mass goes. So if I take it to Earth, we have again tracing out our cycle, and we can see that it's moving quicker. I'll make a larger spring constant, so that's going to be a stronger spring, so more difficult to stretch. So there we get our full oscillation up and down, so that's our period. The time that takes, check it again, So again, about 1.5 seconds. So again, very rough and not a good way to do it experimentally, but it just gives you the idea. If we have this wave that moves up and down a lot quicker, then that is your frequency. So that will be affecting the frequency. So this will be lower frequency because you get less passing every second, and then you've got the high frequency there afterwards. So in the in the questions you'll need to use all of these formulas and the ones from earlier. From the previous section, you need to know these ideas about where the velocity and the acceleration are maximum or minimums. There's the links here to kinetic and potential energy. So again, as we're in the last chapter of mechanics, all of the stuff we've done up until now can come into play, and it's important that you will understand what you're asked and know how to get any quantity you like.